Okay, what we're doing here is taking a look at our textbook that we use in Math 100 and Math 105. What I did is I made the recording and I failed to have the microphone on. So this is going to be a voiceover or a sound over. So there's topic 5 of chapter 4, inequalities in two variables. When an equal sign in a linear equation is replaced with an inequality sign, a linear inequality is formed. Solutions of linear inequalities are ordered pairs. So one of the first things we're going to do is to see if ordered pairs are true statements in a inequality. But first, let's look at what we're talking about. So there's a blue line, which is a linear equation, and the ordered pairs along that line are the solution set, and there's an infinite number of solution sets of pairs along that line. But when we have a linear inequality, it's not just the pairs along the line, but it's a whole solution region that I'm shading in right now. So any ordered pair within this solution region are solutions for that particular inequality that we're showing there. This is the background of what we'll be doing. So determine whether 1, 5 and 6, -2 are solutions of this. And we're going to use the slides supplied by our textbook here. And if we substitute into the first inequality, -2 is less than 5. That is a true statement. And in this one, if we substitute, again, those ordered pair items, we get a false statement. So the first one is a solution of the inequality, but not the second. Now again, whenever we do a line graph, we divide our rectangular coordinate plane into half planes, and the line of the equation is actually the boundary line. But now we're going to do some replacement. Rather than use an equal sign, we're going to use an inequality sign. And here's our first graph. Now, as we look at that, what form is that sort of in? Well, that is sort of in the form of slope-intercept, which I will write y equals mx plus b, but my pen wasn't working too well, so let's write it again. And we call this equation equation 2, slope-intercept. Y equals mx plus b, where b is the y-intercept and m is the slope. So notice there isn't a y-intercept there, so our y-intercept is 0. It's going to go through the origin, and our slope is 1. So let's make a graph of it here. There we go. So it goes through the origin. Our run is 1, our rise is 1, and we put a dot there. Let's do it right. A dot at the origin and a dot at 1, 1. Okay. Now when you're doing MATLAB, this works out very well. But notice this is only the points along the line. Where is the rest of the solution region? And it's where is y greater? And we're going to do what is called a test point or a trial point. And the point I'm going to choose is 0, 2. Now we're going to put that into that inequality and see if that's a true statement. So x is 0 and y is 2. Is this a true statement? Is 2 greater or equal to 0? And the answer is yes. So that is the region we shade. Now there's another way to do this too that I'm going to go over right now. And you'll see that here as well. For instance, as we look at that sign, it says a positive y is greater. Well, whenever you see a positive y is greater, we're going to shade above the line. And that's what we've indicated. So the answers are along the line and above the line. That's what this means. Now, when we make a line in our tool palette, there are two types of lines that we can make. If we only have an inequality, we make a dotted line. And you'll see that from your choice of tools as you pick it up. A dotted line if it's only an inequality. A solid line if it's also equal to. And we'll go over techniques of graphing too. They have a couple of nice slides coming up. So once again, put it in slope-intercept form. If y is positive and it's greater, you shade above the line. Or you can use a trial point, a test point. Now, if you made a point from the other side, and they're going to show you that, that would not be true. Yeah, let's go back. Again, all of these test points make that statement true. Okay. And if it's only less than or greater than, it's a dotted line. If y is greater, you shade above. Greater or equal is what they're showing here. Okay, now we are to graph this one. And what are you going to do? Well, the first thing I would do is put it in proper slope-intercept form. So y is less than a negative 8x plus 3. So let's put some lines on our graph. Now these are our axes. First thing we're going to do is plot the y-intercept, which is negative 3. Oh, excuse me, positive 3. Our slope is -8. So 1, 2, 3, a dot right there. Perfect. Now our slope is -8 over 1. So we're going to go 1 to the left. That's 1, 2, 3, 4, 5, 6, 7, 8 right there. And we make a dotted line because it's only an inequality. Now I don't make a very good dotted line here. It's kind of hard to make. But I make my attempt. Okay, dotted line. Not very good. So to help you, I'm going to put a solid line on top just to show you what's going on here. As I said, I didn't have my microphone on when I first did this. This is a lesson I've learned. Okay, so there's my solid line. Remember, it's dotted because it's only less than. Now, where is y less than? Above the line or below the line? Now, below the line is actually to the left. Above the line is to the right. So, below the line is actually where I'm going to shade right now. Y is less. A positive y is less below the line right there. Now I'm also going to do a test point. Let's do a test point somewhere here. And one of the best test points is 0, 0. So if I put that test point into my original inequality, is it a true statement? Think about it for a moment. Okay, let's do it. So that's going to be 0. And -8 times 0 is 0. So we have 0 is less than 3. Is that true? Yes, that is true. So that test point is in the correct shaded area. Okay? And that's where we said, if y, a positive y is less, you shade below the line. And that's what we've illustrated there. Okay, so there's a little summary of it, and they've done it a little bit better than mine. It's a dotted line. Again, the area of solution is under the line because a positive y is less. And if we use that test point of 3 and a 1, that would not make that statement true. So that's the side of not the solution region. You shade the other side. We had chosen 0, 0. Okay, read these to yourself as we go along. They're giving you pointers on graphing linear equations. If we only use a less than or greater than, it's a dashed line. If we use the greater than or equal to, less than or equal to, it's a solid line. And these graphs will consist of a half plane where one will be shaded, that's your answer region, and the other side will not be shaded. They're going to give us a second slide. So again, if a positive y is greater, we shade above. Positive y is less, we shade below. And there's our slope-intercept form. And they're telling us again above and below the lines. And then if it's only inequality, it's a dotted line. A solid line is used when you have an inequality with an equal sign as well. Okay, let's graph this one. First, we want to set up our axes. There's our y-axis, and there's our x-axis. Now, what is our y-intercept? Well, our y-intercept is -1. So we put a dot at -1. Now, what's our slope? 1/6. Now, it's rise over run. So I've always said we do the run first. It's positive, so we're going to go 6 to the right. We go up 1. And what type of line do we use? Dotted or solid? Well, dotted. And it's supposed to be a straight line anyway. Now, where do we shade? It says y is greater. Do we shade above or below? Well, as you see, we're shading above. Now, let's do a test point. Our origin, if that is 0 and that is 0, is 0 greater than -1? Yes. So our test point is in the correct half plane. And there it is. And that's what we had. Okay, take a look at this inequality now. What does this remind you of? Well, it's actually a modification of formula 6. X equals A, which is a vertical line going through A, which is your x-intercept. And right here, it's x is a -3. So it's going to be a vertical line going through -3. Is it going to be solid or dotted? Solid. And where do we shade? Now it says x is greater. So is it greater on the right, where numbers are positive, or greater on the left, where numbers are negative? And it's going to be greater on the right, where the numbers are positive. X is greater than that. So there's the part that we shade. And again, it's a solid line because all those ordered pairs on that line are part of the solution set. And there's a nice graph for you. Now in this section, we're going to do what is called systems of linear inequalities. We're going to use 2 of the lines. So what do we do? Well, we have to graph each line. Now you could use x and y intercepts, but I like to use slope intercept form. So I'm going to convert both of these inequalities, as you see right here, to slope intercept form. I transpose the x. On that side it becomes negative. My y-intercept of that one was a +3. Now here I'm going to transpose the y to get the y positive, and I get this equation, and then I wrote it in that form. So let's make some axes, and now we're going to plot first the first equation. I'm going to use red to indicate the first equation. There's my y-intercept. My slope is a -1 over 1. So I go to the left 1, up 1. There's my red line. Now here I make a little error. See if you can spot the error. I should have used a dotted line for this. And I do find that as we go on, and I'll change that. Now for this one, I'm using a solid line. My y-intercept is -3. My slope is 1, so I go over 1, up 1. I just put a couple of points there, over 1, up 1. There's my second line. And there at the x-axis is my point of intersection. Now, for something like this, these are all intersections. So I'm looking for where the lines intersect. So I'm using this technique of drawing little arrows to indicate the side I'm going to shade. So for that first red one, I'm shading above the line. There you go, above the line. For the blue one, I'm also shading above the line. Now, where do these intersect? It's just going to be one of these regions where there is intersection. And you see it's sort of where the yellow circle is, right in there. I'm doing it in green. That is the area of intersection. And all those ordered pairs in that area are solutions for both of those inequalities. That is the solution region. And I point out here very shortly that I made an error in the red line. There you go. I had to make it dotted. All right. Now again, if you make that on MATLAB, they're going to count it wrong. Remember, you have like 95% of it correct. So be careful. You have to determine your line, and in that case, the red one was dotted, while the blue one is solid. It indicates those points along the blue line are in the set. So there's the red, there's the blue, and there's the intersection. And they have this one much better. And I'm just reviewing what I've already said. All right, now we have something a little different here. This is an inequality with y. And the equation for y, do you remember those? Those are equation 5. Y equals b. And these are all horizontal lines. So we're going to have two horizontal lines once we set up the graph, one through -1 and one through 5. Those are our y-intercepts. So there's our y-axis. There's our x-axis. And we'll put in our two horizontal lines. One at 5. That would be x is 5. Now, of course, these should be dotted. So what I'm going to do is just erase that a little bit so it makes a nice dotted line or dashed line. You have that tool. Now we're going to have to do some shading. Where do we shade? And again, this is intersection. Well, it's y is greater than -1 and y is less than 5. So we shade right in the middle here. In a sense, this is an and, intersection. Seems like a silent movie, and we're adding some talking to it. I can see that I'm recording because if I looked at my microphone level, it moves back and forth. Okay, so there's our area of intersection. Now, in some of the systems you're going to be working with, sometimes it's more than just 2 equations or inequalities. You might have 3 of them. And where they intersect, these points are called vertices. That's the singular. A vertex is the singular, vertices is the plural. And here are your 3 inequalities, and they shade toward the inside of them. That is your solution region. Any ordered pair within that pink area is a solution for all 3. And the vertices are right there. You could also solve these vertices by, doing equations simultaneously. And here is an excellent review. Let's look at the 6 different types of problems that we have solved. And they're going to give you an illustration of each one. Here is a linear equation. Remember, it was conditional. It had one answer. Now here's an inequality. Here, this had a particular point of sort of where it started, and then all those other solid points along the number line are solutions. Then we had a linear equation in 2 variables, which was the graph. Now 2x plus y in standard form equals 7 is represented by that pink line. That line is an infinite number of solutions for that particular equation. If we made it into an inequality, we have the points along the line as well as the half-plane solution region. Notice a positive y is greater, shaded above the line. And here's something from chapter 3 where we did system of equations, where we looked for intersection of those 2. That had a unique ordered pair, and one we just took a quick look at, where we had 3 inequalities, and the solution region is in the center, and we had ordered pairs that were solutions to all of them. Okay. Well, I think we're getting toward the end of the tape, and this is an unusual one. I'll be very careful we don't not record in the future.